Hi. So this video is going to be a boost converter design video where I'll go over the design of a basic boost converter with the components and waveforms selection. So we'll start off with some assumptions that we're going to make. And if you are from UBC Solar, which is who this video is for, I've added them into this boost converter file. This is in the pass section. And you can see the assumptions I've made here. We're going to start with an input voltage of 60 volts. And this is just because our power supplies are 30 volts. And so we can stack two of them and get 60 volts. So that's 60 volts here. We also have an output voltage, and we're going to assume 100 volts for now. This is not for any particular reason other than I want to actually just have something boost up to 100 volts, and then that way we can measure that. Our switching frequency, this is a little bit nuanced. A higher switching frequency means that you can use smaller components, but you're going to have greater losses due to the switching losses. 100 kilohertz seems to be a good level, so we're going to stick with that at 100 kilohertz. What else do we define here? Oh yeah, output power we're going to say is 210 watts. Again, this is just based on the power supplies that we have, and this is kind of a reasonable number that we came up with. Where do I have it here? 210 watts. Our efficiency, we'll round this down a little bit, so 98% is going to be our efficiency that we're going to start with. Stupid thing. So efficiency is going to be 98%. This is what I think we can achieve. It might be lower than this. It'll probably be lower than this, but we can start with this for design, and we can, work backwards from that when we come to it. What else? Voltage ripple and current ripple. So voltage ripple is going to be the ripple that we see across the load or this capacitor here, basically how much it's going to be rippling like that. And the current ripple is the same sort of thing. So the current, we're talking about the current through the inductor here. So the current ripple is the same. It's going to look kind of like that. And we're saying how much is allowable between the peak and the trough here. So if it was, for example, 20% is what we're going to use for the inductor. That means 20% from the top to the bottom. This is as opposed to 20% above the average, which would be that value there. So let's write that down here. A voltage out ripple of, let's say, 2%. This is kind of just arbitrary. For this project, 2% is high, but not insanely high, so we'll stick with that. And the current through the inductor ripple is going to be 20%. And this is normal. Even higher could be normal. As long as it doesn't go, as long as the current doesn't go below the x-axis. So if this is the sort of positive current here, as long as the current stays above it, it can kind of ripple a lot, and we don't really care. Higher ripple, higher allowable ripple means we can use a smaller inductor because it doesn't have to store as much energy between each cycle. But it causes problems elsewhere, so we'll stick with 20%. This is all of the assumptions, and you can see them here. These are all just set values. So 60 volts input, 100 volts output, 100 kilohertz switching frequency, power out as 210 watts, and an efficiency of 98%, output ripple of 2% peak to peak, and current ripple of 20% peak to peak. So the next thing we're going to do is we're going to look at this boost converter and actually determine what some things going on are here. So the first thing we're going to determine is the duty cycle. So the duty cycle is basically what we're sending to this MOSFET to switch it on and off. This MOSFET is basically just a switch, and we are sending a signal to it of when to turn on and when to turn off. And that signal is just going to look like a square wave. A duty cycle of like 90% would be something like this with very brief off times. And a duty cycle of 50% would be an equal on and off time. And we're going to determine this just by Googling what is the duty cycle of a boost converter. And we find that a boost converter has a duty cycle that is going to be based on its input and output voltage. And that's going to be 1 minus V in over V out. In our case, this is going to be 1 minus V in, which is, again, 60 volts, over V out, which is 100 volts. And you can check my math on this, but this should be 0.4. That means we have a 40% on cycle and a 60% off cycle. And so I'm just going to call this our switch. And in our switch, we can look at what that signal going to the switch is going to look like. And I'll do that in maroon here. So we're going to have an on cycle, and that's going to be followed by a little bit longer of an off cycle. So hopefully that's clear that that's 40% on and 60% off. Not a best drawing here, but just to make it clear, this is what we're talking about as T time on. And this is what we're talking about as the time off. And we can actually calculate these times based on the switching frequency. So we have an assumed switching frequency of 100 kilohertz. And let me just pull up a calculator here. So that gives us a switching period of 10 microseconds, I think. Yes, that's correct. So 10 microseconds is our switching period. I'll just put that here as well. T equals 10 e negative 6 seconds, which is 10 microseconds. All right, so that is our signal that we're sending to our switch. So we're sending it on for 0.4 times, so I guess that'd be for 4 microseconds, and then off for 6 microseconds. And we're doing that on and on and on and on. We can follow from there what is going to happen when our switch is closed and what is going to happen when our switch is open. So let's start with the voltage across the inductor, and let's look at that. So because it's a passive component, let's do this in a different color. So let's do this in red. So because it's a passive component, we're going to mark it this way, and our current's going to be in this direction. And we're going to start when the switch is on, so the switch is closed. If the switch is closed, that means this is a straight line. That basically just means that we're connecting this point here is the same potential as this, if this is a straight line, right? All of this is going to be the same potential. So if this is this, and this is this, then we can see that the source voltage is just being put across the inductor directly. That means that we're going to have some positive value, and the positive value is going to be the source voltage. So let's just mark that as some arbitrary line here. So this is going to be, let's just mark it as Vs initially. And then we can look at the opposite. So what happens when this switch is open? Well, when this switch is open, that means that this is basically non-existent. All of the current must then flow through this branch. That's going to activate this diode. So this diode is going to be on. There'll be a straight line here. And then that means that this point here is going to be the same as this point here. So on the output. Let's get rid of some of this. Oh, I got rid of too much. Yes, okay. So this point here is going to be the same as the output here. And again, the ground is going to be here. So the voltage here is going to be V out, and the voltage here is going to be V in. So the voltage across the inductor is just going to be V in minus V out, because we're going from this side to this side. So that is going to be, V in is going to be 60 volts, and V out is going to be 100 volts. V out is always going to be larger because it's a boost converter. That means that our voltage across the inductor is going to be actually negative in that period of time. So while the switch is off, the voltage across the inductor is going to be the input voltage minus the output voltage, which is going to be some negative number. It's actually going to be less. I kind of exaggerated that here, but it's going to be less than our input voltage because our output voltage is 100, our input voltage is 60, so 60 minus 100 is negative 40. So that's like 60, this is like negative 40. And we'll just do Vs minus V out. Not very good drawing there, but you get the point. And it's just going to follow like that. So that gives us the voltage of the inductor. Our next waveform we're going to look at is the current in the inductor. And I've kind of squished myself, so I'm going to open this up a little bit, move this down. Let's move that down to there. And there's a few things about this inductor current that are going to be useful, because we're going to know certain things about it, but we aren't going to know exact values until we kind of draw out the waveform, and then we can add those later. So let's start with the basics. Well, we know that the current from the source here, let's mark it as green. So the current from the source, let's call that I in. And let's just talk about the average current. So the average current from the source, or all of the current from the source actually, has to travel through the inductor. Any current that's generated here has to go through the inductor. There's no other path. It just has to go there. So we know that the average current through the source is going to equal the average current through the inductor. And that's useful because the current from the source we can actually calculate. And we also know it's a positive value. So I'll kind of draw that here as a dotted line. So we know that this is going to be our average value. And we can calculate it over here because we know that our P in is going to be our P out divided by our efficiency. And we can reformat this, which is going to be I in times V in. And we know our power out, so we can leave that, and we know our efficiency. So that's going to equal the same thing as there. And then we can reformat all this and write that I in is going to be our P out divided by our efficiency, all divided by our voltage in. And you can see that I have done that here in the Excel sheet for this. P out divided by efficiency divided by V in. We'll see what it is here. So 3.57. That's good. So we know that that's going to be 3.57, or I in average. Okay, so that's good for the average, but what does it actually look like? What is the shape of it? And from here, we just go back to basic physics of what is the equations for an inductor. And we know that for an inductor, we have that VL is going to be, so the voltage across the inductor is going to be the inductance times the derivative of the current through the inductor. If you've had Lenar's, this is burned into your brain. VL equals L di dt. So this tells us something because we know this, and we don't know this, but we know it's a constant. So we know that the voltage across the inductor at any given point, because we have this waveform we've just calculated out here, that's this. And we know that this is going to be a constant value. So we can see that the derivative of the current, and that just basically means the slope of the current, right? Basic derivatives, right, is going to be linear because it's a constant. So this is going to be linear. We don't know if it's going to be positive or negative, but we know it's going to be linear. And we can see from here, and that is also just because the voltage is a constant. So at any given moment, the voltage is a constant. Like it changes values, but at any given moment, it is not increasing or decreasing. Its derivative is zero. So that tells us that our slope has to be either just a straight line up or a straight line down. And we can use the equality here. The slope is going to be positive when the voltage across the inductor is positive. So the voltage across the inductor here is positive, so the slope is positive. And then the voltage across the inductor is negative here, so the slope is going to be negative. And I can keep drawing out some things here, but we know that it's going to be centered around this dotted line. So that's not really good, but basically the amount of time it's above and below, like the amount of space here, is going to be the same for the positive and the negative cycles. So that is the current through the inductor. And we don't necessarily know how much it's going to peak at, but the clue here is this term here, the current ripple, which is peak to peak. And this is the current ripple in the inductor. So we know that between the peak and the bottom here is going to be 20% of the average, which is this. So we can actually calculate these values. We know the peak and we know the trough. Now let's look at the current through the diode instead. This one's a little bit more simple. When the switch is on, so closed, all of the current can either go through the diode or it can go through this short circuit here. And the short circuit is lower impedance than the diode, so all of the current goes through this short circuit here. That means that no current is going through the diode. Pretty obvious there, but yeah. Let's use blue. So while the switch is on, there's no current in the diode. What about when the switch is open? So when the switch is open, all of the current has to flow through the diode. In the case of like all of the current coming from this node here has to go through the diode. One second. Okay. I'm back. Where was I? Oh yeah, current through the diode. So when this is open, all of the current from this node here has to go through the diode. There's no other path for it to go to. Any current built up in the inductor, this inductor is going to wind up. It's going to shoot all its current through the diode. That means that this is going to match the waveform of the current in the inductor. So let's just reference that. That's this. And we know that this value here is actually going to be exactly the two values that we see. So it's not like it matches the shape or it's off by some value. It is exactly the same amount of current. So we can just slice and take this down here. So we know it's going to be off. It's going to turn on. It's going to go down like that. Hopefully you can see that that matches. And then again, off when the switch is closed because it all flows through the switch. Up, down, across again, and that's going to continue on. So that's pretty straightforward. And now we're going to look at, this is supposed to be IC, current in the capacitor. Because this will help us derive, basically the two things that we need to find are the size of the inductor and the size of the capacitor. So this will help us find the size of the capacitor. So let's start with kind of drawing out what's happening here. So we have the current in the diode, which we found here. So I'll mark it in blue. That's that one. Capacitor is a passive element, so we'll mark it, we'll use its purple color, but it's going to be like that, current going down into the capacitor. It does supply current at different times, and it takes current, but we'll just draw the direction as this, down through the capacitor. And then we have the current in the load, which is going to be actually a pretty much constant value. And this is not actually a constant value, but we're going to assume it's a constant value. Because if we don't assume it, we can't actually solve this. So this is basically a constant I out. And again, we can just get that from the P out and the V out. So this is going to equal P out 210 divided by V out, which is 100. So that's just given here and here. So that's the I out, which is a constant, and we have the current into the capacitor. So by Kirchhoff's current, we know that ID, write that down here. So ID, the average current in the diode, is going to equal the average current in the capacitor, which actually has to be 0. If it was positive, that means this capacitor would always be increasing in voltage. If it was negative, that means this capacitor would always be decreasing in voltage. So we know over time for this voltage to stay constant, because this voltage is the same between these 2 points. For that voltage to stay constant at the load, which is what we want, the average current in this has to be 0. And that might seem a little bit counterintuitive because we're trying to look at what the current looks like, but it'll make sense in a second. So we know that the average current in the diode is going to equal the average output current. So I out. And we know furthermore that the instantaneous current in the diode is going to be equal to the output current, which again, like we've said, is an average value, is constant, plus the current in the capacitor. And from this, we can see pretty obviously here, hopefully, that I see the current in the capacitor at any instantaneous moment is just going to be the current, I'll go back to blue, current in the diode minus the current at the output. This is a constant value. And we know the shape of this. So we actually have all the information here. All it is that, so I'm going to take this piece here and add that really quickly to this. So the average value is going to be I out. So we can take this whole curve here, the shape of it, which is ID, that's this one, and we can shift it down by the output current. So a constant value there. So that's just going to be shifted down like that. And we can look at IC here, which is going to look identical, except shifted down. Let's redraw that. Identical, but shifted down. So where this I out would be is now this line here, the center line. And since this has been shifted down by I out, this value here now has to be I out. I out. So that's this basically value here. So whenever the switch is closed, this is kind of intuitive. This is basically saying that, well, when the switch is closed, for us to maintain this constant voltage at the output, we have to have a current supplied from somewhere, which is I out, and that current can only come from this capacitor. So this diode is off, so the current is being supplied from the capacitor, and because we've defined current as positive through this way, it's going to be a negative current from the capacitor, and it's going to be all of the current because no current can come from anywhere else. So hopefully that kind of provides some intuitive explanation. But yeah, that's I out. The values here can all be calculated just from whatever value is here, which again is the same as what is this, minus I out. So everything's just shifted down by I out. So let us, now we can use this data basically. Everything that we have so far, we can use to calculate the size of this capacitor and the size of this inductor to achieve the desired behavior, which is basically the ripple here and the voltage ripple here, which I haven't drawn actually, but we can still use this current waveform, which is easier to obtain than the voltage waveform. We are back. I'm going to be calculating, first I'll start with the inductor. So let's pick a color here. Let's go with red because that's what we're using for the inductor. And we'll be using this waveform here, and we'll just write what we know about the inductor. So VL equals L di by dt. And we'll be using these two waveforms. So the important thing here is, well, we have VL at certain moments, and we can sort of see that this can be viewed as like a change in current over a change in time. Calculus teachers might disagree, but in a straight line, it is true. So we can take any point. We can either take between this point and this point and look at the voltage at that time, the change in current, and the change in time. Or we can take this point and look at the change in current, change in time. Theoretically, we can use any point that is along these, but you'll see why this is useful. So let me bring this down here and rewrite it. So, and I'll write it with the deltas, and I'll write it in terms of L. So L, our inductance, which is what we're trying to calculate, is going to be VL. And specifically, we're talking about VL in the on time. So VL in the on time is going to be this section here. And what is that? Well, that's VS. So let's write that, VS. Then we're going to go multiplied by dt and divided by di. But instead of multiplied by dt, we're just looking at actually the change in time here, right? So the change in time here is going to be just this, t on. Yeah, I think that's obvious. So basically we're saying this di is a delta, and so we're just looking at this section in time, which is the time when the switch is on. And we're looking at the voltage then, the change in current then, and the change in time then. And we're saying, well, the change in time is just going to be the time for that interval, which is t on. So again, we're multiplying because we're bringing that over here. So t on and then we're going to divide by di. So this one is where we're going to take that useful thing about the fact that we're choosing from this point to this point. Well, what is the change in current here? Well, that's going to be this distance here along the current axis. And we've actually defined that. That is 20%. Well, 20% of what? Well, it's 20% of our average, which is current in. So 20% of I in. So I'll write that here. 20% of I in. And that is the average input current. That's pretty straightforward. So basically we have our source voltage, which is 60 volts. We have our time on, which is going to be, again, because we know our switching frequency, our time on is going to be 10 microseconds times our duty cycle, because we're only on for 0.4 of that. So 4 microseconds on. So that's going to be that. And then 20% of I in. And I in is given by this formula here, in case you don't remember. I in is power out divided by efficiency. So that's power in divided by our voltage in. And that is all shown here. So we have I in, and we can see here our D is actually calculated as well, 1 minus V in over V out. And our L here is V in times T on divided by IL ripple, which is that 20%, times our I in, which is that 3.57. So I won't calculate it out here because I've done it in the Excel sheet, but you can see how that is derived here. Yeah, so then we'll get the capacitor will be next. So the next thing we're going to look at is the capacitance. And we can actually just use this section here. So I'll use that same color, and we'll take a look at this. What do we know about a capacitor? Well, we know that the current in a capacitor at a single moment in time is going to be equal to the capacitance times the derivative of the voltage with respect to time. C dV dt. And again, we can do a similar kind of thing where we look at a certain section of time and we take the delta V and the delta time. So because I already did before, I'll just quickly rewrite this. C is going to be, we have two choices of time. Well, we can either choose the on time or the off time. The on time is a straight, nice line of current. The off time is a changing current that's going to cause a bunch of second derivatives and stuff, which we can't actually use the deltas in the same way. So this is just going to be I out. Actually, it's negative I out, but we're just looking at magnitudes here. So C is going to be I out. Now we need the change in time, which again, like I've said, is the time on. We're choosing this section to look at the deltas. So T on. And we're going to divide by our change in voltage. And you can see we haven't even drawn out the voltage waveform, but we know what the change in voltage is. It's going to be same sort of trick we did here. It's going to be 2% of the average output voltage. And there we go. We know this, the output current, yes, we know the output current. We know the time on. We have 2%, which is our number that we've chosen up here as our ripple. And we know our output voltage, which is 100 volts. So again, we can go to our spreadsheet, see that calculation here. I out is 2.1. Our T on is that 4 microseconds. Our output ripple is 2%, and our output voltage is 100. And because these numbers are a little bit weird, in the Excel sheet, I've actually just created a little formula that gives them their actual values. So you can see with the parameters that we've inputted here, we have 336 microhenries and 4.2 microfarads. So I hope this was useful. This is the purpose of the video. I just wanted to go over how to derive the component values for a boost converter, given some assumptions. So we've done that. We have the capacitance and we have the inductance. In future videos, I hope that I make, I will be talking about how to derive the efficiency of this converter given certain values. And then we'll go through component selection, how to select an inductor, how to select a capacitor.